So I'm going to ask you for some of the problems that we've done from earlier this week, but now we're going to go and compute the change in entropies of those. So get your notes ready. Right? So this was the diffusion problem. I think it was something like this. Oxygen and I'm not sure if it was helium. And then you were given some pressure, volume, and temperature. Here you're given some pressure, volume, and temperature. Anyone has that? How many people are left? Oh, wow, only 7. Today we didn't have that high of an attendance, huh?
Yeah, I mean, I think probably everyone's looking at the videos later.
Yeah, that's right. They're like, well, you know, when I watch it later, I can fast forward his blabbing on and on and on, get to the real stuff. Okay, so P1 was 4 atmospheres. V1 was 1 meter cubed. T1 was 400 Kelvin. P2 was 2 atmospheres. And then what was the final answer to the final pressure when they combined, the gases combined, and then the final temperature? T final, and then we can call them P final and T final.
326.53 Kelvin.
326.53 Kelvin, and then final pressure.
2.83 atmospheres.
Okay. Let's find the change in entropy of the universe in this problem as the gases are mixing. Do you guys think the entropy of the universe is going to increase or decrease overall? So the helium's temperature is going to increase, right? So because it's going from 250 to 326, the helium, by virtue of heating, its entropy increases. By virtue of it expanding, its entropy also increases. Oxygen, by virtue of expanding, its entropy increases. But by virtue of it cooling, right, its entropy decreases. So because of that, the change in entropy of the oxygen is one part of the change in entropy of oxygen is negative. But because it's expanding, it's positive. So you see, it's got 2 things going on. But overall, when I add all those 4 things, should the entropy increase or decrease?
Increase.
Increase, definitely. Definitely, definitely. That's what the second law of thermodynamics states unequivocally. Yeah. So the change in entropy of the oxygen, okay, is this isothermal, adiabatic, or isobaric, or what?
It's not, none, no?
Yeah, it's actually free adiabatic, they call it, because there's no heat. But technically, in this case, the oxygen is receiving heat from the helium, and it's expanding. Let's see. When we did it, we solved it as it's not isovolumic either. Let's see. It's expanding. The pressure is dropping. Hold on, yeah. I think it's none of them.
Yeah, it can't be adiabatic, so it's none of them.
Oh, it's a bit different than when the gas expands. Only, let's say you have only oxygen and you have nothing here. It's just vacuum. Then the gas expands and its temperature stays the same. In that case, that's called free adiabatic because nothing is putting heat into it, but it's more isothermal than adiabatic because as it increases, its temperature doesn't change, you see. So I would say even though it's called free adiabatic, it's more isothermal, you see, because its volume is increasing, its temperature staying the same as its volume is increasing, right? So that's more isothermal. Now here, it's none of the above because as this guy is expanding, helium is giving it, oxygen is giving heat to the helium, and the helium is receiving heat. So its temperatures are changing. So it's not isothermal and it's not adiabatic. I mean, the whole thing is adiabatic because no heat is coming from the surroundings, but not for each particular gas. So then when we're doing a change in entropy, we got to start from the beginning. dQ of oxygen over T, which is dE oxygen over T plus PdV over T. I'm not sure if I could use, you see these three equations that I just had? The NCV, remember the NR ln? So I don't want to jump and try to use one of those because it might not be any of those. So then we're going to have, this is going to be NCV dt over T plus PdV over T. This one, when I integrate it, that one is going to be NCV ln of T2 over T1, delta S of the oxygen, plus PdV over T. As it's going this way, the oxygen, neither its pressure nor its temperature are constant. So how can I integrate this here? PV is equal to nRT. P over T is equal to NR over V. Okay, then I can just replace P over T as NR over V. NR over V dV. Then that'll be NR ln of V2 over V1. Oh, you see, it's a different formula. And I can't combine them to say, NCP because V2 over V1 is not necessarily T2 over T1, right? This would be equal to this only if the pressure is constant. Do you see what I'm saying? If it was isobaric, see, if this process was isobaric, V2 over V1 would be the same thing as T2 over T1. Then I could combine them. Then I'll have the equation for an isobaric process, NCP ln T2 over T1. But this is neither isobaric nor isothermal, nor adiabatic, nor isovolumic, right? So that's it. So then the change in entropy of the oxygen, okay, the number of moles, did we have that? What was the moles of oxygen? we probably calculated it, right? Or I could just simply do this times this over N over R times T, right? Did we calculate the number of moles, or did we just leave it as because I could also do number of moles is PV over RT. Yeah, I could do number of moles is P1 V1 over RT1 times CV is ln T2 over T1 plus P2 V2 over no, I could still do P1 V1. P1 V1 over RT1 or ln of V2 over V1. Okay, so then change in entropy of the oxygen is going to be P1 is going to be 4 atmospheres. V1 is going to be 1 meter cubed over what value of R should we use? This is atmospheres of 0.08205. And then the temperature initial is 400 Kelvin. And then 1,000 meter cubed is 1 liter, right? So 1,000 meter cubed is 1 liter. So that's all of this. Oh, and then CV is, what was that? Oxygen? What's the CV? Oh, that means the R cancels. I don't need R. Because CV is going to be, if this is oxygen, the CV is going to be 5 halves R, right? 5 halves R cancels R. So actually, I don't need this. I just need temp. Let's see. I just need 4 atmospheres is the pressure. The volume is 1 meter cubed. I need, no, the temperature is 400 Kelvin. But okay, actually, I don't even need to change this. If the R and the R cancels, if the R and the R cancels, oh no, I need to convert it to pascals. Yeah, I need to convert the atmospheres to pascals. The R cancels. The T is 400 Kelvin. This is 1 meter cubed for atmospheres. Okay, so then 101.3 times 10 to the third pascals. Then you have 5 halves. Then you take the ln of the 2 temperatures. What's the final temperature of the oxygen? 326. The initial temperature of the oxygen? 400. You see, like that. So this is 4 times pascals divided by the temperature times 5 halves times ln of this. But this is going to come out negative because the temperature is decreasing, right? But then the next part, P1, V1, the R will cancel again. And then over T1. So then that's going to be, I guess I could also factor that out, PV over T. So then I can have 4 atmospheres, 1 over the temperature, which is 400, times change it to, right, times ln of what? The volume, the ratio of the volumes, which is a ratio of the total volume at the end. The oxygen occupies is 3 cubic meter over the original volume is 1. You see, that's why this and this are not the same, because it's neither isothermal nor isobaric. So I could factor all this out. Delta SO2, 4 cancels with this, makes it 100. 100 cancels with this, makes it a 10. And then 10 times 101.3 is 1013. So then I can factor all that out. That's gone, that's gone. And then I'm left with 1013 times 5 halves ln of 326.53 plus ln of 3. That's it. Here we go. Ooh, so you think the oxygen lost entropy? It could be that this is bigger negative than that. No, this is still bigger. Wow. Times. Ooh. Interesting problem. Joules per Kelvin. It gained the entropy of the oxygen is still positive. I would have been okay if the oxygen lost entropy because the helium would have gained it more eventually, you know. So, but it did end up being positive. That's interesting. Okay, now what's going to be the situation for helium? We don't have to, you start from the beginning. This number is going to be different, right? For helium. So it's going to be, instead of 4, the helium was at 2 atmospheres. Instead of a volume of 1, it was a volume of 2. And it was at 250. 250 times 101.3 times 10 to the third. Okay, so it's like this. The pressure times the volume over this times pascals. Factor that out. Then you have 5 halves. Oh no, helium is not 5 halves. What's the CV of helium? 3 halves, right? 3 halves. ln of, what's the final temperature? 326.53 over the original temperature of helium, 250. Right? Plus ln of what? It starts at the volume of 2. So it starts at a volume of 2 and it increases its volume. So you see what's happening? Its entropy is increasing because it occupies a larger space and because it's now going faster. So both of them are positive. Wonderful, man. God, these are lovely stuff. $326.53 divided by 250 ln times 1.5 equals plus, then take the ln of 1.5. 1.5 ln equals times 101.3 times 1000 times 4 divided by 250. Ooh, its entropy increases a lot. 1306.456, right? So now they combined change in entropy is the sum of that. Let's see. Yeah, so when gases combine, of course, their entropy increases a lot because now we don't know where they're at. It's very hard to separate them back to where they were. You see what I mean? Imagine you have a table salt at home and somebody didn't realize it. They took the sugar, the container of sugar, and they mixed it with the table salt. Could you imagine the change in entropy of that? Oh God, it's like, forget it. Try separating the sugar, container of sugar and salt. Try separating them. Forget it. I would just throw that away. The change in entropy is like, it's probably just like, I don't know. How do you even measure that? If you have equal particles of salt and sugar, and now they're all mixed, the entropy increases by tremendous amount, you know. Try to separate them, it's impossible. Okay, now let's go to one of the other ones.